All right, let's start. Do you have any questions? Okay. So, where were we? So, last time, right, we were talking about stock modeling. Okay. And I guess, so first of all, right, several things to keep in mind. That you don't need modeling for everything. Now, of course, the amount of derivatives that we need model to price, right, are a lot, right? Actually, it's not that common to find, right, options that we don't need a model. But because of that, right, and the fact that we don't, if it's a universal pricing, then it's quite important, and you want to keep in mind, right? Certain special cases, right? So you don't become pedantic and say that you always use some kind of model to price things. So the forward contract, right, requires no model at all. Okay. This comes from basic pricing principle. So that, because of this example, right? Conversely, you also want to think, why is it that what is it that model does for you, right? For us, in terms of pricing, right? I mean, okay, fine, right? There's a certain model like this. There's a certain product like this, right? That requires no model. So when for other products, right, like the call option, right? So you want to think about why, okay? Now, again, this why is sort of like not that easy to explain. I kind of explained it a little bit last time in terms of replication, right? So at the end of the day, it boils down to the fact that this is a nonlinear function of S, okay? And pricing itself is a linear activity. So if you have a linear product, sure, pricing is straightforward. If you have a nonlinear product, right, and I guess it's a vague term here, but the more nonlinear the product is, right, the more complicated it could be, okay? So anyway, but at least try to appreciate why we need a model in case of such derivatives. And because then you ask, when you ask this kind of question, right, then there are more questions that you should ask. For example, how to model, okay? What kind of process do you use to model? And along the line, it kind of is connected to, right, what do we want the model to achieve? Again, I do know that, you know, probably these are the last questions on your mind, right? When you take a course like this, or, you know, just go through a program, because you just want to learn the model and use it, right? And then you know, go get your job. But on the other hand, right, exactly asking these kind of questions will help you understand, right, your model and be deeper about all aspects of it. And right, the fact of life is that, right, I mean, there's no single model that can do everything. And so when the situation calls for a different change, okay, or some kind of modification, if you don't understand deeply about, right, the aspect of modeling or why you use your model, then obviously you cannot adapt to a new model, because, you know, for you all models are the same, and you can't tell the difference between one thing or another. Okay. So again, like I said, these questions are not just, you know, idle academic, you know, questioning, but they really are practical. The more you can ask these kind of questions, the better you will become, okay, in terms of your job as a quant. So anyway, right, so then let's go back to the very basic model that you were taught, right, on day one of this kind of courses. the binomial model, right? And investigate what you learned there. So the binomial model, right, is very simple. It can be drawn even with a picture, but the picture itself kind of hide the, the stochastic nature of the model, which is okay. So right, you might see something like this. This is a binomial tree. Okay, and now if you want to kind of write down some sort of stochastic formulation, right? Sk plus one conditional Sk will be, right, Sk times some kind of, right? I will first write like this for now, right? Where Xk will be U, right, with some probability, and D with some probability. All right. And so, first of all, you should recognize that something like this is almost exactly like a random walk. All right. Of course, I know random walk is, stepping forward and backward, right? And here is multiplication. Well, obviously, that shouldn't prevent you, right? Some transformation would lead you to a random walk right away. And so, again, when you go out there, right, even in popular literature, right, I think there's something called a book called Random Walk on Wall Street or something, right? So the random walk kind of behavior of the stock, right, would be somehow inherent in this kind of model. But you want to be careful too, right? Because actually, like I said, the stock itself is not a random walk, right? In the strict sense of the term. So if you use some random walk result on the stock, right, you're bound to make some errors, right? Conceptual error. So what is it that is a random walk here? Okay. And so I kind of focused, right, on this guy right here last time and asked you what are U and D. Okay, I won't repeat the question, and I hope you understand. It's very important to recognize that actually, right here, Xk is 1 plus Rk, right? Where Rk is the percentage return. Okay. Now, why? The reason, right, is you just check the definition, right? So, I mean, yeah, it's percentage return, not percentage return rate. So the definition of a percentage return, right, over a period is the change, right, in the stock divided by the initial price. Okay. And then, of course, right, you plug in this, you got Sk, right, times Xk minus 1 divided by Sk. And of course, right, that's just going to be, well, I mean, I guess, I don't know, right, it's just exactly what we need. Okay, so equals to Xk minus 1. So in other words, right, when you write something like this and this U and D, it actually makes more financial sense, right, for you to write this, right? And then, right, it makes perfect sense for you to say something like this, as n is S0, 1 plus R I, right, raised to n, product, right? Well, you can do K to what you want. K from, sorry, 1 plus Ri. That's it. K from 1 to n. Is it n minus 1? I think n. So first, I guess with my notation is run from 0 to n minus 1. Okay, doesn't matter. But basically, right, the whole point is, the stock evolution, right, is that each time you multiply with the 1 plus a percentage return, then you get to a next price point, right? So when you multiply by U and D, actually you are multiplying with 1 plus percentage return. Okay. So so one more thing, right? Along these things, there is the idea of the log return as well. So maybe I should use a different name for it. So this is Rk for percentage return. For log return, it's kind of awkward to use, different notation for return, but maybe rlog, maybe, right? That would be natural log of sk plus 1 over sk, all right? And in case you wonder, right, percentage return is like compounding, discrete compounding with one period. Log return obviously is continuous compounding, right, over the entire period. So one is like the extreme of like discrete compounding. This is like the other spectrum, right, continuous compounding. And these guys are closely related, and there's some, kind of implication about them, okay, in the Black-Scholes in the Black-Scholes model that we'll talk about. You also kind of looked at them in your homework this week, right? And you're asked to kind of investigate their different behavior a little bit. Anyway, so let's go back to this, right? And investigate. So what's the big deal, you may ask, right? What's the big deal? In the sense that, yeah, I mean, you can call it U and D, or you can call it, right, 1 plus a return, In fact, right, it seems like I'm just making life more complicated by introducing more, right, more symbols and blah, blah, blah. Isn't that just simpler just to call it U and D, right, and go about your day? So yes, right, I mean, actually, if your point is just to use the model, then who cares, really, right? Do this and, do this. But if you want to understand the aspect of modeling and understand what you want the model to achieve, then absolutely you must understand the finance behind your model and the motivation on why you do this kind of model. Okay. So maybe So maybe let me say this, right? In doing, right, this model, doing this stochastic, right, model, what are you trying to say? You're trying to say that, right, even if taking this guy right here, right, you're saying that sk plus 1 is sk stock price in the next time period is stock price in the previous time period times this, magic random variable, right, which is 1 plus rk. Now you may notice and you may not, but these guys are IID. Yes, at least you see something like this in 621, that the random variable that controls up and down are independent. Of course, they're identical because it's all U and D, but they're also independent. Yes, did Professor Larson emphasize this fact at all? No? Sorry?
I believe he did.
He did. All right, cool. Yep, right. It's important. Okay. I don't doubt that he doesn't know it. I'm not sure if you guys remember he said it or something. But yeah, okay. So this is IID. Now that sounds like, again, right, when you are taking the course, maybe trivial, right? Just make life simpler for you. It's deeper than that. Okay. What this really means is that you're saying the return over non-overlapping period. Okay, RID. Now, to make you appreciate this a little bit more, let's ask you a question. Does stock price, right, over different days or, whatever, right, over different period? I guess the word is not does, right? Maybe R or something. If you collect stock price, right, let's say closing stock price, right, over different, different days, right, like you saw on the Python code, our stock price IID. No, right? Absolutely not. Now, what is another term for IID? Also, if you plot a time series of IID sequence, what are you expecting? Anyone know? Again, right, these are visual check, right? For example, that something's IID. So it's not exactly this, but when you see an IID sequence, you can think of white noise. Okay. I mean, typically white noise also requires you to have like, normal distribution or something, but and mean zero. But basically IID sequence, if you look at them, they're almost IID, almost white noise, maybe just shift up and down. All right. And so if you plot a time series of IID sequence, you get something like this. Okay. Just a band of, right, literally white noise, right? Okay. So this is time, and this is the value of the sequence, whatever that is. So obviously, right, when you plot stock price, it doesn't look like this. Yes. So it's not white noise at all. If anything, it looks more like a random walk, but we'll explain why it's actually not a random walk. Okay. So now, maybe the next thing that we look at, right, is this, the why of the model. Or what do we want the model to achieve? And this is where things get a little bit funny because there are many things you can hear about. Yes, but I do believe that, so not Brownian motion. Brownian motion actually is a random walk. The change in the Brownian motion or the Brownian motion differential is white noise. Okay, so dW is white noise. W itself is random walk. So W itself is a integration of the Brownian of white noise. So change of the Brownian motion is white noise. All right. Or you take a random walk, you take the step size out of white noise. So now, what do you want the stock model to achieve? And when you think about it, right, I'm pretty sure you guys haven't thought about this question so much, maybe. And let me say, right, some obvious, or not some obvious, something that people might say like this: to predict the future stock price as as well as we can. Okay. So again, I'm not trying to say that this is a wrong purpose, or I'm not saying that this is a wrong thing to do. I'm just asking, right, in the context of what we're trying to do. So don't forget, right, our job is not to trade. Our job is to price option. Okay. And even to trade, right, we can even question that this is what you want to do to the model to have to begin with. But do you think that in the context of pricing, right, you want your model to predict the future stock price as well as you can? Is that what we're trying to achieve here? Yes or no? Yep, that's why I say this is, quite tricky to think about. No, we don't. Actually, here's kind of the thing, right? If you can predict the future stock price in some way, then actually you think about it, the option payoff is also kind of predicted. Yes, because if you know some ST to some degree, then you should be able to predict this guy to some degree as well. If that's the case, right, then pricing itself is a very different business than what we're doing, which is averaging. Agree? So intuitively, no, right? And in fact, if you could, then option pricing as a market itself is going to be very weird. Okay, but more about that later. So actually, let's go to this, right? In fact, let's go to this topic because I think, right, is kind of fascinated. It fascinates some people. And by the way, right, this is also something that you want to draw a line. The reason is this, right? To ask this kind of question, to ask this kind of best fit, right? And that kind of thing is very much a question in machine learning, okay? Again, I'm not claiming that this is a useless question or anything like that. No, right? They have their places. It's just, is this kind of the place that we use this technique, and why or why not? Okay, because again, right, nowadays you hear too many techniques, too many things, too many discussion. You have to understand where and why each technique is used, right? Because even if you have a very fancy thing, but you use it in the wrong place, then absolutely it just makes no sense, right? Like you drive a car inside a stadium. That's just not the place to drive a car. Okay. So now actually let's just look at this a little bit, right? And let's ask you, how hard do you think predicting the future stock price is? Or I don't know, this is a vague question, right? You know a way to predict future stock price reasonably well. Again, I'm not trying to advertise any stock future prediction here. I don't claim I know any, but there's something that's kind of funny, right? That at least you should be aware of. Anyone? One very simple way actually is to run a regression, just a linear regression actually, of stock price tomorrow on stock price on the previous day. Okay, so this is 1 day, right, lag or something like that. So basically, you predict the closing stock price of tomorrow based on the closing stock price of today, right? And you do it for a time sequence. So basically, right, this is actually technically not a regression model, because regression, you have to kind of use an explanation, right, explanatory variable to explain something. So here you use the stock price to explain itself. And that actually is something along the line of an AR1 model. Okay. And that is the topic of time series, which you should be aware of if you're in this business. And I think in econometrics 2, you might be exposed to that. Now, one thing is you want to ask how well, right, does this do? Okay. Yeah, so the word predict, right, is a very, very funny business, right? What does predict mean? Okay. So let me ask you this, right? If you run a linear regression, how do we evaluate a linear regression? And I'm not trying to say, right, and this is actually a big question too. But let's say, just say offhandedly, right, if you have to pick some very quick criterion to evaluate a linear regression, what do you do? This is a deep question, all right? I'm not saying that this is an easy question to answer. There are many things you have to look at. But if you have to look at a quick and dirty way to evaluate a linear regression, what do you look at? Well, you guys all took econometrics 1, right? Or at least you should know linear regression. Yeah, right. I mean, I'm not claiming R square it tells the whole story, but R square is a quick and dirty way to look at things, right? And to answer, I guess, for teammate questions, right? R square is sort of like an average error. So yeah, so we we look at the percentage of fluctuation, right? We explain using our model versus the fluctuation remaining, right, which is the error, and see how well that captures. And so when you run this thing, right, the R square will be around 90%. And if you look at any linear regression, R squared around 90% is pretty impressive. Okay. But does that say anything about prediction? Well, again, right, I guess go back to Fatime's question, right? that may not do anything because first of all, right, you're just kind of looking at the stock price on average. And second of all, why does this model do so well? The reason is because, right, stock price are, this is not impressive. I mean, in terms of what it does, because stock price are highly correlated. What I mean is, right, autocorrelation function, right? Again, a concept in time series, the autocorrelation function, right, of the stock price evaluate with a one-time lag is really high, right? And if we have a high correlation, of course, when you use regression, you can capture, right, the fluctuation very well. So there's nothing impressive about this. On the other hand, right, actually, this idea, by the way, right, I'm trying to use a 1 day, right, kind of time step to explain this, because if you run it on 1 month, I think the the prediction will be less because the gap will make your correlation be weaker, right? But anyway, let's just take this analogy a little bit further, right? In the sense that, isn't it reasonable for someone to model something like this? Okay. So you know what I'm trying to say, right? So basically, right, this is the random term, right? This compare with your model, the binomial model, which is, right, and this is the random term, right? And this is just a coefficient from the AR1 model. Now, and if you want to, you can throw in some sort of like, so maybe I should do alpha and beta, right? Just to make it like this, okay? So these are the coefficient from linear regression. So if you throw in an alpha, it's technically not an AR1 because, AR1 doesn't have the constant term. Anyway, right? So maybe I'll say something like AR1 like, right? But anyway, right? The question is this. You do know what I'm trying to say. That I hope you know what I'm trying to say, right? That why not this model? Why not this model? Is it any worse than this model? Okay. Is it any less reasonable than this model? What do you think? And in fact, right, if anyone who comes out of linear regression training, they would say, yeah, I think I would like this model much better, right? I mean, I don't know. They're more familiar with it, right? Why this? All right. So again, this goes back to what I was trying to say about, right? You need to understand what you want your model to achieve, how you model, why you model, right? Because again, right, someone will ask some kind of like funny question like this, and it should stop you because, right, you can't tell, right? Why this and why not that? Why not price with this model, right? Besides the fact that you say that no one else does it like that, but you have to admit, right, that's not really the answer. So okay. So now here are several things you want to keep in mind, right? First of all, do not forget the purpose of what we want to achieve. We're not here to predict stock, right? Even in whatever sense, right? In machine learning sense, whatever. No, we're here to price, okay? So a model that does well in explaining or predicting the stock in whatever sense may not be of any use for us because again, we're not here to predict the stock, right? And maybe let me not use the word predict, right? Because that's actually not a very precise word, to fit a pattern on a stock price, right? That's not what we're trying to do. So maybe a better goal that we can say we try to capture, right, is maybe, right, a better way is we try to capture the so-called the statistical property of the stock price using our model. Okay. Now, if you are not used to this business, you might think that what I'm writing down here is not much different than what I'm writing up here, right? But actually, it is quite different. To capture the statistical property is, I don't know how to say this, but is to look at the nature of the stochastic movement of the stock, right? You're not really interested in fitting the value itself. No, you're not, you don't care what the actual value is. I mean, you might use it, but what you're trying to do is to really come up with some model that somehow explains the randomness of the stock internally, okay, intrinsically, rather than relying on the data to tell you what to do, okay? So in this sense, right, you realize that this model is very much data driven, in the sense that, right, you have to see the realized value of the stock to get alpha and beta, right? This model we can discuss in the classroom without seeing any data, because, right, I mean, anyone would agree that the stock price in the future is stock price in the past times 1 plus return. And so something like that is what I mean by capture the statistical properties, right? You want to understand intrinsically what this model is about, rather than let data drive, right, the model. Again, right, I'm in saying this, I'm not trying to say that these guys have no purpose, right? They have their purpose, but maybe in a different place, right? Now, why? And maybe let us just carry this a little bit further, right? And here is what I want to say, some time series Bayesian, right? Modeling idea. Okay, and again, I think some of you guys, or most of you guys, may be taking econometrics too, and time series should be covered in that a little bit. But even if you don't see much, I highly recommend that you try to look more into time series. It's kind of a very useful knowledge area that you want to know, okay, in this business. Now, what do I want to say here? The first thing is this, right? And time series modeling 101 is this. We can only capture a stationary property time series, let me say. So what that means is this, right? And again, you have to understand what the word stationary mean to understand. So stationary means that the stochastic property does not change with respect to time, okay? So the stochastic property is stable throughout time. All right. And again, right, the word stationary is much more complex than that. And again, I'll let you find out, because again, I'm not teaching time series here to you. But let me give you a very basic example, right? The stock price itself, right? So is a function of time, right? Stochastic properties is just a fancy word to say distribution and that kind of thing, right? So let me ask this, right? Does the distribution of SK stay constant over K? No, actually, no. In fact, a martingale itself, right, its property does not stay constant over time, right? So because a martingale says that the future value condition on the current value is the current value, right? But that actually may not guarantee that this guy behaves exactly like this guy. Does that make sense? Like only when you condition and take expectation back into the past, right? Exactly, right? So stock price itself is, discounting is a martingale, right? But does that mean that the distribution of SK stay constant over time? No, right? Because actually, if you look at the expectation of SK, for example, right? What do you hope, right? Actually, expectation of SK, let me just say changes, right, through time. To begin with, right? And by the way, I mean, I'm trying to say this, maybe in terms of the physical probability. But yeah, I guess maybe in terms of Fatime's kind of remark, right? Let me say this too. Sure, right? Maybe then you can say, well, but if I look at risk neutral, right, probability, then they stay constant through time. Point taken. But actually, here's another thing, right? Does the variance of SK change through time? And actually, this guy, you cannot avoid this. Okay? Because even if you have the risk neutral probability, right, which will help you stabilize the expectation, the variance of the stock price will change through time. Why is this so? Does anyone know why the variance of the stock price will change through time? It doesn't matter if you are under risk neutral probability or not. The variance will change. The reason is this, it's very simple, right? And actually it's an empirical fact, right? The higher the stock price, not about that, but the higher SK, it should be the wider the fluctuation. You can observe this, right? For example, if you look at Amazon stock price, right? What's an average one-day change in their stock price? Because Amazon, I think, is selling around 1,000, or maybe Google, whatever, right? Take a very high stock price. One day change, right? Regular for them, right? A swing could be easily 10 bucks, right? $10 swing. Now, if you take something that has very low stock price, like $5, a regular change for them is what? 10 cents, right? So if you have a stock price as around 1,000, then a change would be around 10. If you take a stock price around $5, then the change might be around 1 cent. Again, right? I'm just making up these numbers. Is this okay? This should be a very routine thing that you observe, right? Now, of course, right? You see, then actually your mind will say, well, that's nothing strange, right? Because of course, the change here relative to the price is not that impressive. But notice, right? That's the concept. First of all, do you notice that you agree that the variance here, right, for this guy is much higher than the variance of this guy? Because the variance here is about 10 and the variance here is about 0.1. Agree? But when you say that there's nothing out of the ordinary for this kind of price level, what are you looking at? You're looking at percentage change. So you're looking at 10 over 1,000 versus 0.1 over 5. Okay? So that's a clue for you right there, that the price itself is not a stable distribution, or it's not an object with stable distribution over time that we can model, that we want to model. Okay? But the return is the stable object. In other words, right, the return of S, right, are more stable, right? Or actually, that's exactly the word, stationary over time. Okay. And we have reason to believe this too, right? In other words, over 2 non-overlapping days, okay, the stock price, the return on the next day should have nothing to do, right? So the return on the one day should have nothing to do with the return on the previous day. And they should have similar behavior. Okay. On the other hand, the stock price, right, next day is not independent of the stock price on the previous day. Is this okay? So, sorry, right? I should do SK+1. So this kind of analysis, right? This kind of thinking shows you that, right? Because you want to capture stationary time series, and time series techniques, right? Exactly, will try to manipulate the time series until you achieve a stationary object. So you may take a difference of time series to get down to a stationary level. So stock price itself, from this analysis, right, is not a stable object to model. So what we want to model, so we start to model, start with the return of S. Okay, so that's the point of the binomial model, and actually any kind of model that we use in pricing. We start to model the returns, and then we rebuild the stock price out of returns itself. Is this okay? Any question about this? I know that some of this discussion I'm kind of skipping over a lot of details, and some of them are more like intuitive idea, empirical idea. But any question about anything I say? Oh, so the meaning of part 2 is exactly to answer this question, right? This is modeling the price itself, right? This is the modeling the price itself. Well, here, right, is the model. So when I do this, the meaning is actually, right, so the meaning is with using this, I will start with model RK. And then I rebuild SK using RK via this formula. Does that make sense? Or, right, if you want, if you look at the time series of this, the error term here may not be IID, actually. It may not be stationary. So AR1 model may not be a good fit for the stock price itself. Stock price does not follow an AR1 model. If you take a time series course, you will see that, right? So here, so basically the problem with this is you're trying to model price directly, right? Also notice the alpha and beta has no financial meaning. What's the meaning of the alpha and beta term here? Okay, here financially, right? You are modeling the return, which makes complete sense. You model it as an IID sequence, like white noise, right? It kind of sounds funny, but you start to model things with a white noise block, IID block, and then you start building things out of the white noise block, like this. Okay. Well, again, right, some of these will become clearer in the future, but I'll give some example, right? So with the binomial model, you model the return, right, as IID, U and D like this, and then you rebuild the stock out of the return. Okay. And you can also have a random walk, which some of you might have seen, right? How do you model a random walk? you model a random walk by model the step size as IID, let's say 1 with probability P and -1 with probability 1 minus P, right? And what's your random walk? So your random walk, X may be, right, is a sum of the step, right? So these are the steps. By the way, right, the word S here just means step, right? It doesn't have to anything to do with the stock. Right? So you model the step, and then you build the walk, which is the position of where you are based on the step. Brownian motion, which we'll look at next. Right? Brownian motion, you start to model Brownian motion by saying that dW is normal 0 dt. Of course, we have to be careful about what this is. And then you build up the Brownian motion from the change in the Brownian motion differential. So actually, this and this are very similar idea, except that, you know, one is discrete and one is continuous. And that's why Brownian motion is a continuous time random walk version. Finally, the Black-Scholes model. Now, you would have seen Black-Scholes model like this. dst is mu st dt plus sigma st dwt. All right. Now, again, the expectation is you should not have seen this before, you know, if you have not taken a course like this, but I don't know, right? Have anyone seen this Black-Scholes model, the Black-Scholes model like this? Okay, no, no one else? No one has seen Black-Scholes model like this? Not at all? Okay, that's fine. So this is a very, very standard way to write the Black-Scholes model, okay? And actually, where it comes from is actually like this. All right. So in fact, right, what you're saying, what you're seeing, this is the percentage return. This is the rate of return. And this is the volatility, which is the rate of the, you know, it's a little bit more complicated. You should take the rate of the variance and divide by square root, right? So sigma dt, right? Sigma squared dt will be the variance, the return. But anyway, right, you see that at all levels, the return is where you start, right? And stochastic calculus, by the way, right, what you will learn in this course is exactly how to rebuild, right, the price of the object, the random. So here you try to rebuild the random walk out of the differential. Here you try to rebuild the stock, right? Because notice here, I'm not giving you the stock price, right? You need to know how to, from here, you need to know why the stock price will be this. Right, from this model. That's stochastic calculus. By the way, right, so calculus, right, integration. So we are trying to integrate, right, the differential, the change in the stock, right, into the original price. But that's what I mean by rebuild, right? And again, that's the math, the technique to rebuild. But the financial idea, or, you know, the fundamental modeling idea is that we start from modeling the return. Why? Because the return is the stable object. The return of the stock is IID over time. Okay, and that's where we start. That's the I don't know, the explanation, right? The foundation of why we are modeling this way. Any question? Okay, so now, right, so you have to also play around with data, right, and things like that to also appreciate, right, the idea in time series and that kind of thing. And so exactly, right, this is why, right, it's good to play around with this stuff. And going back to now, I can explain to you, right, besides the idea of collecting, right, stock price and option price using Yahoo Finance, right, it's a very good playing ground for you to test whether, right, your model or the observation of the, what we say holds or not. And let me warn you, right, here, our goal is not to predict stock price or fit stock price. So a lot of times the stochastic probability, so stochastic properties that we try to capture may or may not hold, right, with the data. So you have to be very perceptive and you have to think hard on what the model is trying to say compared to what the evidence is saying and try to see if the model is reasonable or not and why, okay? And so it's not just about fitting a perfect fit and that kind of thing, right? It's just more complex than that. And so first of all, right, this is the price itself. And like we see, right, that the price has a dip here, right, at the pandemic, and then keep climbing up. But now, just a look at this picture. Can you already see that, right? Stock price itself is not a stable stochastic object. Yes, I mean, just look at this time period, right? The mean keep climbing up, right? So definitely this is nothing like an IID sequence, nothing like a stationary sequence. Agree? Now, if you look at, right, so here is the picture of things in comparison. So the time series technique, the most basic one is to take the difference, all right? In calculus, the equivalence of that is taking the derivative. But of course here you just take the difference. So, you don't divide by the time interval. So, but notice one thing, right? If you take the difference, so this is not the return yet, right? The return will be the difference divided by the magnitude, all right? And so you see that even after you take the difference, this looks, even without, right, taking the kind of normalizing with the stock price, already it looks more like white noise. It looks more stable. Yes? So this is why this is the object of model rather than this from a time series point of view, because this is more stable. Now, of course, right, this guy's jump out like a sore point. Now I'll address that later. But right, like right here, right? And of course, if you kind of normalize it by right, stock price is even better, right? Notice the scale. So this is the point here, that you want to model these guys rather than the stock price itself, okay? So we specify a distribution for the return, and then we rebuild the stock price out of the return, right? In terms of data collection, is the opposite, right? We collect the stock price first, and we calculate these guys later. But in terms of modeling, you model these guys first. One of these, right? These are equivalent, and then rebuild. Any questions so far? Now, right, of course, this guy, right, sticks out like a sore thumb. And of course, what is it, right? What is this trying to tell you right here in terms of the finance lingual? How would you say, how would you describe this? What are you seeing here? Abnormal, of course, but what quantity are you seeing that's behaving abnormally? this is the map of return, right? You see what high swing, what captures the swing of sorry, I just said what captured the swing of return. Volatility, right? This is a period of extremely high volatility. And then volatility kind of comes back to a little bit more normal, right, compared to that one. Of course, right, there's still some spike of volatility right here, you see. But, right, at least compared to this, right, this is extremely volatile period, right, extremely high volatility, okay? Now, exactly because of something like this, or even minus that, you look at this, right? That is way too abnormal. This is a critique of something like a Black-Scholes model, where notice in Black-Scholes, what do? We say that the volatility is constant, okay? So sigma is constant. While here, right, clearly sigma is not constant, and you might even need to do there's a model called regime switching, right? You need to switch the regime because there's no way sigma can gradually go to like, something high like this. Anyway, that's more advanced model. But the point I want to bring up is, of course, we're just going to study Black-Scholes model in this course, but you want to see what the data is telling you versus what the model is trying to capture, and be honest and say how well, right, the model is capturing the data. In different sense, right? Here, I emphasize we're not trying to fit the stock price in any way. We're trying to capture the stochastic property. And even that, right, with this guy right here, definitely Black-Scholes won't do it. But anyway, right, you must see the real data to at least have a sense. And then one thing, right, remember I keep talking about the IID independence. One fun tool you can do, right, is to look at the autocorrelation. And by the way, right, so this is the correlation of the, oh, sorry, I don't do this. I don't do the stock price. This is starting with the price difference. So just the correlation of these three guys. And ideally, if they're white noise, then the correlation should be small, right? The autocorrelation with different lag should be small. And we don't see small autocorrelation. And that probably has to do with this unusual time period here. Okay. So autocorrelation is just to check independence. I mean, not truly, because correlation is not about, but almost there, right? You should see small correlation, autocorrelation, right? If you really truly have a white noise. And so, right, one thing that we learned, or you see is, one thing I want to say is, right, the time period where you use to model is highly important, right? It's the same model, but it might work over some time period. It doesn't work over some other time periods, right? So here that was 2 years, right? Now we just do 1 year observation. And so you see, right, 1 year looks much better, much better, much better, much better, right? This is much more believable to be a white noise sequence, all right? And when you look at the autocorrelation, right, they're all small. So nothing like a highly dependent kind of nature, right? By the way, right, the dependence nature of things are very, very serious, meaning that there are some people who do some models on, long-term memory, stock model, that kind of thing, and how to price under that. That's even more advanced, right, than a model that try to change volatility, I think. Anyway, right, that again, you want to be aware of what phenomenon the data is trying to say, and you try to be aware of what model will capture that phenomenon, right? I just want to point that out here, right? Over this time period, it seems like the Black-Scholes might do an okay job to capture it. Any questions so far? So, right, actually, this raises yet another question. Then the Black-Scholes model seems no good, right? Because, there's some time period where it obviously does not apply, and there's some other time period where it applies. I mean, what's the point of studying it or what? In fact, right, maybe I can tell you, I you study because it's very popular. But why is it still very popular, right? I can tell you that it's still being used a lot in the industry these days, at least, for a quick check, that kind of stuff. Why? Why do we use Black-Scholes model when we see something like this in data?
Because normally the volatility is somewhat constant.
A good point, Kareem, right? But I'd like to say that a little bit, right? Yeah, good point. But when you say normally, right, notice about the time interval, right? We kind of did go a little bit further away, right? We did go all the way back to 2 years to see this kind of highly dependent behavior, right? If you, and actually notice for most options, what's the usual time window for expiration? Six months to a year, right? Usually for the most fluid, right, kind of highly traded options, right? 6 months to a year. So during a time window like that, you could expect, like what Kareem said, right? The movement is not super volatile. So, right. But on the other hand, of course, right, you can ask then, how do you price option around this period? Well, if around this period, you can talk to any quant, right? Most of the models will fail. You have to think of how, right, you can adjust your model if you're unlucky enough, right, to be in this time, right? Of course, that's when the market becomes crazy. Nothing works as expected. But you can, one thing I want to bring up is Black-Scholes is pretty okay for a short-term window, because during the short-term window, right, things hopefully are more stabilized, right, rather than when you scan through a long time period. Is that okay? So that's one reason. Another, of course, is just convenience. Black-Scholes is super easy to use. So as long as it's a reasonable fit and it doesn't take so much time, right, compared to some other more sophisticated model, it's kind of, kind of pay off. Then you can still use Black-Scholes, right? But at least you should be able to justify why, right? That you use Black-Scholes over this time period because it seems stable, all right? Otherwise, people can question, and you have to admit that it may not work. One more thing, right, I want to bring up is the time window, right? The above deals with daily data. You can redo everything with monthly data, and you see a different, right, resolution, first of all. So, and things will change, right, when you do with a different resolution. But one thing I want to bring up, right, besides the behavior of the time series itself, is this, that one thing you want, right, out of the Black-Scholes is the mu and the sigma, right? Or at least you want to make sense out of those. So the mu, right, for a daily return is always 0. Doesn't matter how good that name is, right? We are looking at S&P, right? And even over a good time period, right? Over this time period, the daily return is almost 0, right? It's just too small to count. So you only start to see return at the monthly level, and people usually, right, will average that into the annual level, right? When you say, right, they say return is, I don't know, 8% or something, like 12%, right? That's an annual number, right? I mean, a monthly number, right? Even over an extremely good period, right? Wait, why do I do oh, I do to, yeah, it's still extremely good, right? 2018. I mean, look at the stock price. The average monthly return is 1%. Yes, 1.3%. Of course, right, that annually, that will be like 12, 13% or even more, right? So the point is, you won't see return at small time window, right? You must go through a longer resolution. Why don't I do annual data, right? I guess you can play around with this, but one thing is, if you do annual data, right, then we don't have enough data to average, right? Because at the end of the day, you have to average things out. You take the mean of the sample, right? Mean of the return. If I do annual, then I need to get at least maybe, I don't know, 20, 30 years, right, worth of data for each of the return of each year, right? That is much more, that's much less reliable. So, and of course, right, maybe I'm just interested in the annual return over the last 3 years or so. So the way is, right, probably is to take the monthly return and then annualize it, right? Annualize it like the formula I talked about in the homework, right? Okay, so the resolution is something you want to pay attention to as well. By the way, right, suppose I want to estimate sigma, okay? The volatility rate, let's say monthly sigma, right, rather than annual sigma. You can also look at that. Can you suggest a way for us to calculate sigma out of the data? How would I do that? How will I take the sigma? How will I get a sigma out of the data?
You can look at the price difference and find the mean of that and like calculate the average difference from the mean
No,
of the
right?
price difference.
So the price difference is definitely not the returns, right? Be careful with that. Price difference is not return, right? First of all, the mu is the average of what? Mu is not the average of price difference, right? Mu is the average of returns, right? Here is literally 1%. So look at, right? I took the average of return, right? And notice how the log return is slightly below the percentage return, you see, which is interesting. There's actually a practical thing about this, that if you want to make your portfolio look more impressive, you should always report percentage return, okay? And you don't tell people what kind of return you're calculating so that your portfolio seems more impressive than it really is. Or who knows, right? Depends on what measure, right? Anyway, that's one story. But mu is the mean of the return. And sigma is the what? What's sigma? The variance. So you can just take the variance of this return, right? And take the square root, that will give you the volatility. Understand? So you can get the volatility out of this data as well. And then a fun thing for you to do is to look at different companies and try to calculate their variance, the sigma, and see if that follows, right, your intuition that you think, I don't know, Facebook is riskier than Google, right? Is it true that volatility of Facebook over the last 3 years is higher than the volatility of Google? Okay, but at least you should understand the concept, what the parameter means and how you can estimate it out of the data. Any questions so far? All right. So let me talk a little bit about this idea. Historical estimates versus implied estimates. In particular, I want to talk about historical volatility versus implied volatility. Okay. So remember, right, last time I said, right, you must not lose track of this, that one of the goal of pricing, right, or the activity of pricing is to help you derive implied information about the company, all right? From the derivative price, okay? So in particular, you can get the implied volatility from, right, the pricing model. Now, what we just discussed, right, is a way to get volatility, right, from the data. Yes? Are these the same thing? No, right? In fact, this is what we mean by historical volatility, right? Volatility you get from observing data from the past. Now, so I kind of seem to make a big deal out of this thing, right? I say that's the goal of pricing. Now, let's ask the question, right? If you already have historical volatility, why spend more time and work to derive something else like an implied volatility? What's the point? What's the reason? All right. So that's actually is a slightly deep question. It's not that deep, but you have to think of where implied volatility comes from, right? Comes from. It comes from derivative price. Yes. And what is derivative price about? Derivative price, right, is about future payoff. Okay, because right at the current moment we look at, right, hopefully you're not looking at past derivative, you're looking at the current derivative, right? Right now, the derivative price right now, which is about the future price of the stock of the company. Yes. So when you do that and you incorporate those information in, and then you do the pricing and you figure out the implied volatility, this is forward-looking or future information. It's about the future behavior of the stock and how the market thinks the stock future will behave. This, of course, right, is from the past. Now, in terms of evaluating how the company is behaving right now, or how the market is thinking of the company is behaving right now, which one is more relevant? Yeah, right. I hope it's clear that the implied volatility is much more relevant because, right, the market is actively trading the derivative, right? Obviously, you don't want to look at the derivative that no one's trading, but if the market is actively trading the derivative price, remember, right, that factors in their evaluation of the company and how they think it will behave into the future. Therefore, when you do the implied volatility, this contains the information of how the market is actively evaluating the company right now. While, right, historical volatility is about the past 3 months, whatever, 3 years behavior of the company, which, right, might have gone through some time period that is of no concern to you, right? For example, like the pandemic, whatever, that may not be happening right now. So it's still some useful piece of information. But if you want to capture market sentiment or whatever that is, that they're thinking about the company, right? Implied volatility is, right, is kind of like the most updated information, all right? And if it is even forward-looking. So, right, understand that's why, right, the pricing. But you should at least be aware of these two objects that both are implied volatility. You should know what volatility is. You should know how to get your hands on both of them, but you should know the difference and why we care for each. Any questions so far? Okay, so right, let's talk a little bit about the homework of this week. So I'm just going to say real quick that you will be asked to find implied volatility using real life data. So you will be asked for that. So I'm not so sure, right? So it's historical data. So historical data are used for what they call gosh, what's the name? I'm bad with names these days, like running check on portfolio performance. What's it called? Back testing. Yeah. Things like that, right? So I guess you have to use different things for the right purpose. That's all, right? Historical data definitely is very useful for you to run tests, to run scenario. There's historical analysis, or what they call it, historical simulation or something, right? That's one thing. Now, as far as volatility is concerned, right? If you are interested in how the company is behaving right now, or how the riskiness level of the company right now, yes, that's what you're concerned with. Then again, right, by the way that you look at implied volatility, or by the way that exactly implied volatility is constructed, everyone must agree that that's a much more informative measure. That's all, right? Who knows? I mean, if you are interested in how the company was behaving in the past, then past behavior, right, is exactly what you're looking for. You understand? So you have to see what you want to do. But in terms of evaluating the company's riskiness right now, then implied volatility is a much more relevant piece of information. All right. So sure. So what I want to say is probably you can use Black-Scholes formula there, but you need to use your own numerical method, okay? And because at some point you will have to solve for the volatility sigma. One thing I want to say is this, right, very quickly, that I will ask you to use the binomial model as well. I'm not, so maybe Black-Scholes too, but we'll see. So if you want to use binomial model to price, all right, here's a question. That basically, right, if you use binomial model to price, then the price, right, will be a function of what? S0, right? R, K, T, right? But then U and D, right? That will be V market. So, but then the goal is to find implied volatility, right? So in other words, where is volatility in the binomial model? How do you find it? How do you get it, right? Notice the benefit of Black-Scholes is that sigma is baked into the model, right? But in the binomial model, you don't have sigma, you have U and D. So how do you get sigma out of this? If we use binomial model to price. All right. So I'll tell you the answer, right? And we'll talk more about this next time. But there is a parameterization that is very useful in binomial model that you should know about. You would use U to be e to a sigma square root of delta t, and d to be e to a minus sigma square of delta t. All right. And this is actually discussed in whole. I think, let me give you the reference real quick. Section 13.7, matching volatility. All right. The point is, you use this parameterization, then the volatility of your stock model, of the binominal model, will be sigma. All right. So the volatility of a stock price under this parameterization is sigma. I actually already posted a file, right? Let me show you real quick and then we'll call it a day. Can you see this? Parameterization of the binomial model. So here, right, if you're curious, we'll discuss this next time, but you can look at yourself. That I show you that with the parameterization I just told you about, exactly the volatility, right, by simulation is sigma. Okay, so you can trust that that's the right one. So now you can use this parameterization to find the implied volatility, right, using the data from Yahoo Finance. That'll be the homework for this week. Okay. Any question? All right. If not, then I'll see you next week. Okay.
Thank you.